Hello, everybody, and we're very happy to welcome you all to today's webinar with Huawei Fusion Solar. My name is Andy Colthorpe. I'm the Deputy Editor-in-Chief at Solar Media, working across our channels, including solar technology website PV Tech and energy storage news. We will be looking today at the vitally important role played by the inverter in the safe, reliable, and efficient operation of PV systems, with a particular focus on future-proofing inverters designed to deliver utility-scale applications. That includes, of course, hybridization and pairing with energy storage systems, or ESS. Now, while developments, innovations, and design advances within PV cells and modules get a lot of attention, and rightly so, we also often hear across the industry that inverters are the brains of the PV system. A solar power plant can generate lots of wonderful, clean, low carbon energy at zero marginal cost of generation. But without the right inverter technology, its operation will never be optimal, and generation output and efficiency cannot be at their maximum levels. So perhaps there is no better example to learn from than from Huawei FusionSolar's SUN2000-330KTL inverter. The state-of-the-art utility-scale inverter was indeed the winner of this year's prestigious Intersolar Award, and that's due to its key features, advanced functionalities, and of course, overall quality. We will be hearing today from Hariram Subramanian, who is Chief Technology Officer for Smart PV and head of the Huawei Fusion Solar Competence Center in Germany. Hariram will be talking not just about the SUN2000-330KTL, but also about the principles of design and future-proofing that go into designing it and top best-in-class inverters in general. And we are also very fortunate to be joined by Lewis Kang, who is Director of Renewables and Smart Home at DEKRA, which many of you will already know of as a respected expert organization for testing, inspection, and certification. Our format for today will comprise short presentations from our two speakers, followed by a short panel discussion, which I will be moderating and asking our speakers a few questions. As always, interaction with you, our audience, is very important to us. So please put your questions for today's speakers into the questions tab on the right-hand side of your screen, and we will tackle those in the Q&A section at the end. Now, we can't promise to answer all of them, but we will do our best. And anything we are not able to cover in today's online session, Huawei Fusion Solar and DEKRA will be very happy to follow up and get in touch with you directly to discuss offline. Finally, today's session will be available to view on demand for all registrants a few days after this live broadcast, and presentation slides will be made available too. Once again, thank you very much for joining us, and I'd like to hand you over to our first speaker. Over to you, Harry.
Thank you very much, Andy, for your nice introduction. Thank you to everyone. I hope you are able to listen to me clearly. Thanks a lot for making the time to be here virtually to attend the Fusion Solar webinar. I'm happy to meet you all virtually. As a majority of our global listeners in the industry would acknowledge our pole position in the inverter technology, I would like to draw today all our listeners' attention as I'm going to explore some of our radical innovations from the product from Huawei Fusion Solar, especially about our utility scale latest flagship product, the SUN2000-330KTL series. Actually, there's also another reason for me to be more excited, as this product line has also won the Intersolar award. I'm going to go a bit deep about this product today and provide you with the overview on the status quo, let's say innovation about this product, as well as walk you through on the challenges which the industry is facing and the industry needs now that needs to be addressed at the global stage. As you see, I will focus on three sections. From the challenges, I will talk then to innovation and walk you through the product. And then I will also focus on typical project case studies with the SUN2000-330KTL. We are all facing once in a century transformation of the energy system. And it's completely new from the way the energy is generated, it's transmitted, distributed, converted, and consumed. This means there is an intensified electrification that is happening in various sectors, in industries, as we see now, that renewable energy is becoming the decisive technology, enabling all this electrification, and we are going to see more to come as well. We see here three drivers, especially from the carbon neutrality goals, energy security, to withstand the price swings and also to ease the energy import dependency. Another key driver that we also see here is the technology itself, the renewable energy technology, and the value and the affordability of this technology. There are actually various ways in order to achieve this carbon neutrality goals. We see that as two alternatives. One is at the generation side, where this generation side is basically at the source. Another one is at the demand side or at the load side. As you can see here, various assessments from various think tanks and studies. And everyone in this industry who have experienced the growth of this industry know that there is a steady or an accelerated growth. At one hand, the LCOE is decreasing. We see increased installation capacity, but the industry also have its own pain points, and we see these pain points are also growing. And it's imperative to address these challenges and these pain points today, and also to bring in high amount of credibility into this industry. There are points and topics related to efficiency, reliability, safety, lifetime aspects, various concerns to varieties of stakeholders in the industry. But also there are important topics related to metrics, nomenclatures, verification of these metrics, and definition of these nomenclatures. At the application level or at the solution level, we are seeing a lot of installation in variety of environment conditions. We are seeing floating solar power plants, agri-PV combination, desert conditions, mountainous regions. And all these applications are also asking for or calling for a reliable and a very safe technology, as there are different challenges when installation would happen in a floating environment, different challenges in a desert environment, and so on. And the key challenge, as I want to deliver today as a message, is safety. As you know, we have a lot of power system components in a power plant, and all these power system components and equipments must be resilient and robust and should be carefully designed, especially to satisfy highest safety standards. And not only that, and also to go beyond these typical standards, for example. There are a lot of potential hazards in a power plant. Typically, whenever there is an electrical installation, could be electrical shock, fire, arc flow faults, flashover, and these would affect the electrical continuity, availability, and the reliability of a power plant. In some cases, it is also, let's say, said in various press and magazines of creating economic risk for varieties of projects because of these safety challenges. The second important challenge is the grid stability topics, especially when we would see a lot of power electronic penetrations into the power systems. This topic is of present concern to variety of, let's say, network operators, as well as to utility scale and at the distribution level, at the project level as well. And this needs to be addressed. As traditional power systems would have a large conventional generators, and we see that these are gradually replaced as I speak now, also with the technology, which are basically based on algorithms and power electronics. And these algorithms or power electronics are individual. That means it is actually depending on, let's say, the manufacturing, or let's say depending on the people who bring these control algorithms and the company who bring this kind of power electronics. Since these are control based rather than physical law based, the challenges are also tremendous here to be addressed. In addition to that, there is also a tremendous challenge in the power system, especially in terms of inertia, especially in terms of, let's say, the grid strength and so on. We will also see that later when we go a little bit more into deep dive on these topics. One important topic when we speak about grid challenge is also the location of renewable plays an important role, as most of the renewable, let's say, plants are built, let's say, far away from loads and demand centers. It could also create some potential power transfer issues. People typically call it as weak grid. Basically, it is a topic related to voltage stability and long distance power transfer capabilities. Actually, there are various methods and proven ways to solve this through algorithms, manufacturing inverters with some specific control measures to handle these kind of low grid strengths. And also with this high percentage of power converter coupled generation, the characteristics or so-called dynamic characteristics of the power converter will affect the entire power system as well. And this will be reflected in power quality, in stability, power system stability, in oscillations and scenarios that is very, very unique, especially when these algorithms starts to play around with power system components, yeah, or transmission system and distribution system components. We will also see those topics today. Let's go a little bit more in detail, and let me summarize the SUN2000-330KTL innovations. And as I said, this product is actually the flagship product, which has got the Intersolar 2023 award. And there are certain reasons behind this. And typically, we will see from our customers' perspective various reasons, but we summarize this as higher yields, smart O&M, safe and reliable product, as well as grid supporting features that has enabled us to get this award. Overall, from an application perspective, when we would look how the system solution would look like for a utility scale power plant, there is also certain offerings from us, from the smart PV converters, or let's say the controllers, the smart PCS, the smart string ESS, smart transformer station, and smarter power plant controllers, including the monitoring platform and portal. The solution that you see here is encompassing a variety of innovations. For example, power line communication, fuse-free concept, robust grid support features to work in variety of grid situations, and also product level innovation like smart self-cleaning fan, multiple amount of safety features, multiple level of insulation diagnostic features, IP66, and also satisfying highest amount of cybersecurity, and everything put together is helping to save the electrical BOS cost for an utility scale power plant projects. We will review these basically one by one. And what is important from what I see from the industry and also from our customers whenever I discuss is the revenue loss, especially due to derating. And this is seen as a very critical topic right now, as we see many inverters are installed under challenging ambient temperature. And this could especially affect the revenue stream due to harvest reduction on derating and so on. From the product side, we did advanced testing scenarios and under stringent conditions to prove a constant, continuous, stable operation without derating for 24 hours, especially compared to many other Me-Too products that is available in the industry. Other key aspect is the compatibility to the mainstream PV modules, thereby bringing in a high amount of flexibility for procurement and easy spare part management, especially when we are talking about 182 modules or 210. The inverter can diligently support a varieties of scenarios and to get different optimal DC-AC ratios. And in addition to that, the dynamic MPPT performance, the state-of-the-art input level handling of the power point tracking is also able to maintain full output power with very highest power conversion efficiency. When we would look into the DC side innovations, we were the first one to integrate a proven technology called a smart DC system, or SDS in short. This is integrating basically a tracker intelligence through optimal tracker control, especially for project that uses trackers and systems around trackers. We have incorporated in this a smart controller with more intelligence that is enabled through deep learning, and which is helping to go to the right tracking and angle, thereby improving the project harvest. There are a variety of case studies done globally to prove these features. And actually, our optimization algorithm have shown capturing more light in challenging terrains, in different irradiance conditions. And there are a lot of proofs that is coming also from our customer side, getting benefit from this smart DC system. Then the important thing is the day when we came with our products to the market, the first product, for example, one of our key goal was to bring in a zero-touch maintenance. Yeah. And this zero-touch maintenance, or we call it as zero-touch O&M, is now enhanced with smart fan, with automatic self-cleaning without manual intervention, thereby saving significant O&M cost also during the project's lifetime. Smart PV management with multi-level management is helping to get diagnostics and visibility in various granularity, ranging from plant level, array level, device level to the string level. So it goes very deep, and this is what we call it as refined management with exceptional detailed information from real-time data, and also providing alarms and statistics and big data analytics for O&M teams for your projects, basically. One of the key innovation with our clients, and especially O&M leads and managers globally, are fully aware and also fully excited, is the smart IV curve diagnostics. And now with the smart IV curve diagnostics 4.0, which is widely used in variety of utility scale projects and installation, we are able to provide full diagnostics of highest accuracy of PV panels with highest precision here. It's more like a prescriptive maintenance, I would say, where root cause assessment and diagnostic details are well elaborated. These are done through some pattern matching algorithms and big data analytics that is running behind it to come up with, let's say, information and visibility that is typically not possible in a large utility scale power plants. Thereby also bringing in O&M effectiveness here. Some key features which was well recognized in the Intersolar awards is also the smart string level, let's say, disconnection, which is one of the imperative safety feature in our product to identify DC side faults. Typically, the DC side faults are more frequent, and I think all our listeners would know this who are in the power plant business. And this DC side faults are frequent in PV plant, and what is important is to have a technology that would rapidly disconnect the system before the fault and the hazards propagates, basically. And such kind of technology brings the smart controller as a key system component for active safety. Various situations like string fault connection, DC input current reverse flow, internal faults that would or can also happen, are all well addressed through this smart string level disconnection feature that is integrated into the products. Similarly, the SCLD, or the smart connector level disconnection, is the latest innovation into the products that is incorporating an integration of an intelligent temperature sensor in the DC side of the inverter to prevent and protect against any kind of abnormal heating, and also to shut down the system before, as I said, the hazards spreads around other power system components, or the hazard spreads around the power plant. And this is also one of the very key safety feature where we have addressed actually the questions and posed by our customers to us through this smart connector level disconnection. And most of the DC faults, as I mentioned before, are common in utility scale plants. Yeah. And there are other pain points also faced by majority of our customers and majority of the people in the PV industry in the utility scale. That is the precise identification of fault location, as is the so-called. Most of the inverters will do the RISO detection before it feeds into the grid, which is the residue, which is actually called as the insulation monitoring. And we have now brought in a high amount of granularity into this diagnostics, which is done at the MPP level, MPPT level, with high accuracy. And this smart feature is very important to detect and position accurately the DC side faults, which is very helpful for utility scale power plants projects. As many know that we are the market leader in communication, and we are also one of the industry first to bring in the so-called power line communication, or the PLC technology, which has now become advanced with the MBUS system. That is bringing much more stable communication with no packet losses and reliable data for transfer for control application, for power plant controlling, and also for SCADA communications. We have improved the distance to a longer range, and we can also span with this technology broader arrays. For example, we are speaking around about 9 megawatt of long span arrays, and the communication would be very reliable in this kind of, let's say, system in the power plant applications. And we have been speaking about certain product features, but what is also important is the product reliability from the design and the way the manufacturing is done, like through automatic manufacturing, the manufacturing process, the verification and validation process, in order to bring in a robust and a very reliable design to the market. It's not just a kind of a simple thing, as it involves methods like physics of failures, performing different burn-in tests, onboard intelligence incorporation, and even avoiding certain kind of vulnerable components or fatigues. Like, for example, a typical system could have IGBT soldered, but we are talking about press fit pins where the fatigue that happens due to soldering is completely eliminated. So there isn't any kind of cold joint, solder joint issues or soldering joint issues. And also incorporating a full IP66 sealing and the system design is providing a very robust operation in extreme harsh mission profile scenarios and in environments. And we have seen this also being, let's say, evaluated by third parties, like here TUV certification, who have evaluated a power plant and have provided us very interesting availability with around 99.99% availability. And the story or the reason behind it is because of the inverter design, and also because of the robustness in the manufacturing and bringing the product where typical failure issues are eliminated by using fuse-free concept, by not using any kind of, let's say, O&M practices, and bringing in the zero-touch maintenance and so on. There are various reference cases here. And as I initially showcased certain scenarios, we can also see different mission profile with the installation scenario in the largest single PV power plant, where the inverters are running in a very weak grid situation with a short circuit ratio ranging around 1.2. Installation in ultra low temperature, where we would see actually the ambient temperature going around minus 40 degrees, and the inverters are performing extremely well here. Situations like in deserts, where we would see a temperature going above 48 degrees, ranging around 50 degrees, like for situations in ultra large scale projects, and also projects that is happening in floating bodies or in fisheries, and joint project with agri-photovoltaic and solar in locations in Europe as well as locations outside Europe. Installation in a corrosive environment like near to sea coast, what we see is a high salt spray situation and so on. And utility scale scenarios with tracker applications providing higher yields, and also situation in high altitude above 4,000 meters, for example, in Argentina, Chile, and also locations in China, where there is no derating that is happening and the system performing extremely well. One important topic is on grid friendliness. The inverters are able to handle weak grid situations, or a situation where there would be a kind of a high impedance in the network, or typically discussed in technical terms like the short circuit ratio. We would also see locations and installations where the short circuit ratio might go below 2. We are also seeing around 1.2 in these cases, or 1.1, and integrating the grid sensing features, stability algorithms, passivity, and full compliance in fault ride through low voltage and high voltage, and also power system quality through harmonic suppressions and damping is providing this product a complete, let's say, intelligence for installation in utility scale environment. A case is here from Australia where there is a very stringent and robust grid code validation process and a robust grid code verification process after construction. And I am happy to share that we are one of the smart PV string inverter solution here, which has got the full compliance and operation notification with Australia's strict grid code conditions, with robust test and validations, looking into models in RMS and EMT levels, and also looking into the performance on the site at the power plant level. Another interesting case study is a challenge of weak grid, and this is a case study from Heilongjiang project in China. As I said, the weak grid will create certain issues on power system transmission, and this project that is actually working very high amounts of power system stability is having around a short circuit ratio of 1.85, and we are also bringing in power system stability here and cleaning up, or let's call it as providing sync to the harmonics, and also cleaning up the grid and providing high amounts of power system stability in voltage, stability in frequency, and also stability in power angle and so on. Some typical project studies. One interesting project study is the Ali Zero Carbon project with the capacity of 150 megawatt. And this project has incorporated with 330 KTL inverter, all the features like grid supporting, running at a very weak grid situation and providing stable grid conditions. And it also have incorporated all the safety aspects as I walk through today, and also have integrated the zero touch O&M capability or smart fans inside the products. Another interesting project is a combination project with water and PV complementary, very interesting project with a capacity of 1 gigawatts. This project is actually in a very high altitude, and the system is performing extremely well. We see around 4,000 meter altitude here, and there is no derating here at this high amounts of altitude. And the system is also performing with a very good grid stability into the power systems. Another interesting project is a floating project in Fuzhou in China, where we see here a total capacity of 260 megawatt, and this project is giving extreme good harvest for our customers and also bringing in O&M efficiency at this project level. Thank you very much for listening to me and also understanding our innovation. And I hope I have walked through you certain key aspects of our products, and I would be more than happy to also answer any of your questions that will pop up today. Thank you very much.
That's fantastic. Thank you so much, Harry Ram. And yeah, really interesting, particularly to see all the different use cases and types of PV projects. And yeah, obviously a lot of information conveyed in a short action-packed presentation. So we had a couple of questions from the audience whether the slides will be available after the broadcast. Yes, they will is the answer. So you can take a look at those at your leisure and obviously watch the video again. So yeah, thank you again, Harry. And moving on, Lewis, if you'd like to put your camera on and unmute your microphone, we'll look forward to your presentation. So Lewis Kang from DECRA. Hi, Lewis.
Hi, Andy. Thank you, Andy. Hello, everyone. This is Louis Kang from DECRA. Very happy to be here to meet everyone online. Also, thanks for Hariram's sharing. This was very insightful and interesting. Hariram has mentioned that safety underpins the sustainable development of PV power. With the increasing PV module current and the increasing capacity and power of inverters and other key devices. Also because PV application scenarios are getting more and more complex and diversified, it has drawn industry's wide attention on the PV plant safety. DECRA is the world's fourth largest testing, inspection, and certification company. Sorry. There's a... Okay, sorry.
No
Yeah,
problem.
I can switch that. Sorry.
That's great. Seems to be working now, Lewis, yeah?
Yeah, it's okay now.
Okay, terrific. Thank you.
Okay, now I will continue. DECRA is the world's fourth largest testing, inspection, and certification company, and is the largest one in Germany. We aim at becoming a global partner for a safe, secure, and sustainable world. We ensure safety, security, and sustainability in all scenarios of human life, including on the road, at work, and at home. As a third-party testing and certification company, DECRA has long cooperation with Huawei, especially in PV safety domain. Both of us have laid great importance on safety technology study. DECRA tested many products from Huawei for safety, grid code, and cybersecurity. Today, I'm very honored to be here to share DECRA's insights for some industry trends and key findings from the perspective of certification body. My topic will focus on three parts. Part 1, general introduction of safety aspects of a PV inverter. Part 2, the important safety considerations of DC side. And part 3, what's important in cybersecurity. Talking about a PV inverter, there are many different comprehensions of the term safety. In the past, the scope of safety was kind of narrow. We only concerned about personal safety and trigger loss caused by electrical equipment. This is referred to as fire safety, electrical safety, mechanical safety, etc. If the insulation in an inverter is not sufficient, it may lead to electric shock on a person. If the temperature exceeds ignition point of material used in an inverter, the inverter may catch fire. The fire can spread to a wider area, thus cause trigger loss. Later, we started to find that EMC, electromagnetic capability, will also affect our life significantly. What is the risk if an inverter is not in compliance with EMC requirements? An inverter can interfere normal work of nearby equipment when it emits high radiation. The high radiation may also harm human health due to biochemical reaction in human body coming from tiny current flowing in the body. Grid code is another important thing we should pay attention to. Grid code not only qualifies grid compatibility, grid support ability of an inverter, but also prescribes protective functions in abnormality. Grid code concerns many safety aspects like the safety of maintenance electricians when the grid is shut down. The grid codes are evolving quickly following the fast-growing penetration rate of renewable power generation. The quick update of grid codes deserves our close attention. Cybersecurity is a new requirement for inverters. All power plants communicate with grid company in some form. A cyber attack on the communication will make power generation units not work normally. The worst effect can be shutdown of the whole grid. Cybersecurity of power generation relates to energy safety of a country. In the past, only very large power plants were required by grid company for cybersecurity. But as the penetration rate of renewable power generation is getting higher and higher, cybersecurity of distributed energy source is also concerned by grid company and the government. This is a general introduction of the topic that from which aspects we consider the safety of inverters. In next slides, I would like to walk into details of several key points. A PV inverter has DC side, AC side, and communication. In DC side, the ground fault and arc fault have led to most of the field accidents. To address such issues, some new technologies and requirements are coming up. The AC side, however, is not too much different from traditional power sources, especially for utility-scale PV inverters. They both use low-voltage cabinets and transformers to connect to grid. I will not go into details for AC side. For communication, uniform protocol and cybersecurity have been considered very important. The most attractive issues in recent days are about cybersecurity. DC ground fault can cause both fire and electric hazards. The rationale is, if a non-isolated PV inverter is used in a TN system, insulation failure on a PV cable could lead to high current on the grounding path, which will further result in a high temperature in grounding cable or high current in human body. As required by many standards, inverters for use with ungrounded arrays should have means to measure DC insulation from the PV input to ground before starting operation. If DC insulation is lower than limit, inverter should indicate a fault and should not connect to the mains. When the ground fault happens, the maintenance person can see the fault signal and will try to localize the fault PV module. In utility-scale PV power plant, the increasing power of PV inverters and the increasing number of PV strings make such troubleshooting more difficult and time-consuming than distributed power plant. Currently, product testing standards do not require any means for detecting exactly which PV string or which PV module has a fault. But we can go further than what the standard requires. If we have an MPPT level fault detection technology, it can directly localize the fault PV string and could infer which PV module has a fault by calculating from DC insulation resistance. We will be able to find the fault PV module much more easily. This could be a future trend for DC ground fault. DC arc fault detection is required to be installed in a PV power plant by some standards like UL 1998B and IEC 63027. In distributed PV power plant, this arc fault detection and interruption device is usually integrated in PV inverter. DC AFCI works very well in lab. However, it may not work so well on site because of heavy signal noises and complicated scenarios in different PV power plants. Traditionally, only arc current voltage frequency domain is used to detect arc fault. This is not sufficient for complicated scenarios on site. To address this issue, I think AI technology like deep learning with huge amount input data may be used for more accurate arc fault detection. DC disconnection device is used for manually disconnect PV power plant in an emergency. This device is sometimes also be used for automatic disconnection in case of any DC fault. Usually, DC fault happens only on one string. It will be more efficient if we only disconnect the fault PV string itself rather than the whole DC input of PV inverter. Such technique will help save power in a DC fault. Furthermore, traditional electromagnetic release or thermal release of overcurrent protection device can only act when the overcurrent is much higher than rated current. However, usually even the PV string is short-circuited, the overcurrent is only 1.1 to 1.2 times of rated current. Traditional disconnection device will not work in such situation. An electronic disconnection with intelligent detection in this case will be a better option. It can catch and protect slight change of current, even voltage. I think Huawei has made a good attempt in this direction and developed some advanced disconnection devices. One of them has already got DECRA certification. For communication part, I would like to share some best practice of cybersecurity. As some of you may already be aware of, Great Britain added cybersecurity requirements in their grid code. to be connected to British public grid. All power generation units and their associated equipment must comply to certain cybersecurity standard. Radio Communication Agency Netherlands launched an investigation last year into whether PV inverters pose a threat to cybersecurity of the electrical system. The result indicated that many inverters were not so secure and certain means should be implemented to mitigate cybersecurity risk. Among the many cybersecurity guidelines standards, two standards are considered most relevant for PV industry. One is IEC 62443 series, as I showed here. This standard family originally was drafted for cybersecurity of industrial automated control systems. PV inverter is the brain, is a central control device of a PV system. Thus, the standard family can be easily transformed for use on PV inverters. The standard family is combined by 4 sectors, from general concept to policy procedure, then to system engineering, and then to component devices. Sector 4 is for development lifecycle requirements and technical requirements of devices. This is most relevant for devices like PV inverters. Top manufacturers like Huawei adopted this concept of this standard family very quickly and cooperated with certification body for compliance to the standards. In 2021, DECRA issued our first IEC 62443 CB certificate in renewable energy industry to Huawei. IEC 62443 utilizes an approach of identification, analysis, implement, evaluate, certify circle to ensure a development procedure or device comply to the standard. It covers many different risk levels and maturity levels. It is a quite complicated standard and is kind of heavy for products with limited digital and communication functions. This standard, EN 303645, in contrast, is a lighter standard. It was originally drafted for IoT devices and set a baseline for cybersecurity. The standard does not consider too much about the device development procedure. It prescribes separate test items to ensure the basic compliance to cybersecurity. As many PV inverter manufacturers are not quite familiar with cybersecurity requirements at this time, they choose this simpler standard as a start point to ensure a basic level of security. Above is what I would like to share for cybersecurity. Okay, thank you, everyone. This is my part.
That's terrific. Thank you very much, Lewis. And so, yes, I can see that obviously a lot of questions already from the audience, which is terrific. So we won't spend too long on these questions that we have and this discussion that we're about to be having. But yeah, we'll do that, and we'll try and tackle as many of your questions, as I say, as we can. So gentlemen, if you could unmute your microphones again. Lewis, I guess in your case, put your camera back on. Sorry, I know you just switched it off. And unfortunately, folks, Harry's camera was having a couple of technical issues today, so he's very much with us, as you'll be able to hear, but unfortunately we can't see his face today. Great. So yeah, just to start off, Harry, you talked at the beginning that we're reaching a global consensus on the need for decarbonization. Unfortunately, there are some politicians that perhaps are still not quite with that, but obviously in terms of an industry and as technologies, very much the case that the momentum is with renewable energy, and that's a great thing to see. But our area of that is solar PV, and so what percentage or proportion of renewable energy deployments needed for that global transition to decarbonized energy will be solar PV, do you think, according to the experts, but also what is your own perspective, or perhaps Huawei Fusion Solar's perspective on this?
Sure. Andy, I mean, to be very honest, we are looking for 100% of renewable energy deployment, right? So, and this means 100% and also to electrify all the sectors in this. And also to have an ambitious, not just an ambitious, but achievable and reachable target, basically. Yeah. And there have been some studies, some estimates done through International Energy Agency. There have been some, let's say, think tanks who come with some numbers here as well. But before I go to the number, I think what is important is actually the overall industry should see efficiency improvement. Yeah, at the generation side, as I said, also in the demand side. And the target can only be reached, as you said, whatever is required globally in Europe, for example, not just by doubling what we are installing right now, but maybe we have to go even quadrupling, not even tripling and so on. I think the world would add around 1 terawatts of capacity. Maybe, we want to see around until 2030. From the estimate, what I see from International Energy Agency, I see the capacity increase by around 2.4 terawatts, around up to 2027. And what I see from the PV perspective is, as we see a rapid growth, we will see around 60% of all new installed, let's call it as renewable energy capacity, would come from PV, or maybe even more. Yeah. So it's exciting. At the same time, we have to target all the challenges, is what I said. Yeah.
Yeah, absolutely. Thanks, Harry. And Lewis, clearly efficiency, as Harry says, is absolutely vital. And yeah, just generally having a lot more solar PV and other renewables is important. But as you mentioned, safety is absolutely key to that as well. We can't have a reliable industry that isn't a safe industry as well. So you talked about some of those key aspects, but what are some of those aspects of safety that the industry, you think, perhaps doesn't quite pay enough attention to at the moment, or perhaps overlooks and doesn't realize is, as important as they are, really? Oh, you're on mute there, Lewis. Still muted. Is there a problem with your... Oh, there we are. Yeah.
Okay. Thank you, Andy. Sorry.
No problem.
Yeah, I think this is indeed a very good question. In nowadays, actually, we have already had a lot of safety standards for PV. People have known and implemented much more than before for PV safety. In the past, we had much more knowledge of safety for power utilizing devices than power generation units. But as now there are more and more PV power plants, we gained a lot of experience on how to design a system with DC voltage up to even 1,500 volts to be safe. We even find ways to mitigate risks on non-isolated PV inverters with residential current protection device and DC ground fault detection and interruption device. There are more and more new functions in PV system, like integrated ESS, energy storage, like multiple mode inverters working in both grid connection and standalone scenarios. But I believe people will easily find risks and implement safety designs very quickly. However, one problem I have seen in the industry is that I think we lack some system level considerations. Take cybersecurity as an example. I have seen that in many bid invitation documents, it is required that inverter must comply with cybersecurity. Just the term cybersecurity, no other details. Sometimes bid documents will specify the standard to be IEC 62443, but again, there are no other details. It sounds to me like the bid inviter is saying, I heard about cybersecurity and I know cybersecurity is important to PV inverters and PV systems, but I don't know why it is important. And I don't know which aspects of cybersecurity really benefit me. Just do something on cybersecurity, although I don't understand, but it will certainly be useful. The thing is that we don't require cybersecurity because it is popular. We require cybersecurity because we need to. We have found some digital assets are very critical. And we have found that if some communication ports and software services are attacked by a cyber attacker in certain forms, critical consequences will happen. We need to protect them, and we need to mitigate the risks we have identified. So if we consider security or safety from system level, I think we can easily know what details of cybersecurity we should require. Electrical safety is the same thing. When UL 6099B became mandatory, many people told me that inverter must integrate an AFCI device. Otherwise, it is not allowed to be sold in USA. The truth is that DC AFCI is only required in the PV system, not inverter. It can be internal or external of the inverter. You must know why a DC AFCI is required and which location is the best choice to install a DC AFCI in a certain PV power plant design. You must think in system level.
Okay.
A standard for a system for PV system. A standard for PV system, IEC 62548 was published, but did not draw much attention of the industry. So I think in the future, now safety for PV system is like many lonely islands, but ultimately the islands will race and connect to each other. We will see a continent of a whole safety world. Thank you.
Wow. Okay, that's you finished with almost some poetry there, but that was that's a great answer, Lewis. And I think we will have to obviously keep moving on in interest of time, but I really appreciate that. It's a really interesting answer there, and I think it's I guess it's a good thing that these bid documents do include a mention of cybersecurity, but obviously, like you say, the understanding of that is really important. So, I guess we're here to try and help the industry understand and people outside the industry even to understand some of these topics. So, Lewis, in terms of future proofing and future trends in the PV market and technology, let's keep focused on inverters today, but what are some of the things you expect to see being done in the industry in the coming years? And I think actually, Harry, it will be interesting to hear Huawei's perspective on this after Lewis's answer, if that's okay.
Sure.
So, Lewis, if you could start first.
Okay, thank you, Andy. This is a kind of a difficult question. I think that the renewable energy industry is still evolving very fast. It is difficult to predict what the future trends are.
Sure.
I have seen some products with multiple functions with PV input, grid power output, standalone power output, energy storage, and even EV charger combined together. So I think there will be many future proofing products. But for specific topic, utility scale PV, I suppose the important thing for future proofing will be it should be very reliable with high ability to resist against high and low temperatures, dust, water, and other severe environmental conditions needs a long life cycle. The mechanical parts should be very reliable. And it should be designed to be able to detect and protect as many faults as possible, which are in the whole PV system. It also should have some energy storage, charge and discharge function, or at least leave some interface to connect to other device who has charge discharge function. Because even utility scale PV power plant, ESS will be necessary in the future. It should have a uniform communication protocol so that it can report its status to grid and receive commands from grid very easily. It should also comply with common best practice cybersecurity requirements based on experience of the whole industry. This is my expectation of a future-proofing utility scale PV inverter. Thank you.
Interesting. So I guess there's a level of adaptation. I think just as as Harry said in his presentation, putting PV plants in all kinds of different conditions, different grids, and different geographies. So I guess that's a really big part of it, but also the adaptation of all the other things that you mentioned. So yeah, Harry,
Sure.
I don't know if you have. Yeah,
Yeah, I
go
have
ahead.
some points to also add. I mean, from the future trends, from the product perspective, it's always going to go more towards, let's say, utility scale architecture, new architecture. It's going to go more towards high power density. We already talked about reliability, but everything is interrelated somehow or the other. And as Louis said, I like this statement that everybody in the industry is thinking in island, but not as a continent. I think that's exactly what it is, because there is a lack of harmonization on variety of topics. The industry players need to collaborate. When I speak about the future proofing, there needs to be an establishment of best practices. There needs to be maturity models for safety. Test procedures needs to be there. Establishment of process. And it's also very imperative to have a common understanding or common definition, and to have a common nomenclature. As I always see, as also Louis said, some people say, Louis gave an example from cybersecurity, but I can give an example from the grid side. And people say, does it have inertia? Does it do black stud? The definition and the nomenclatures needs to be well addressed to have a common understanding of what is the meaning of black stud here, for example. So the industry needs much to do. The product side, the trends are going more and more towards advanced control algorithms and high power density and efficiency, and reliability. And for future proofing, the industry needs to come together and collaborate.
Yeah, absolutely. That's a great answer, Harry. Thank you very much. And I think I'd like to get your thoughts on one of the main areas of focus that Lewis talked about in terms of safety. So the Huawei FusionSolar SUN2000-330KTL series was an Intersolar award winner. I don't think we can say that enough, obviously. So congratulations on that. But yeah, I mean, with particular regard to safety, and I don't know if this was one of the other factors behind its winning of the award, but could you tell us about some of the key principles or design strategies involved in creating, I guess, not just that series, but the other inverters in Huawei FusionSolar's range?
Sure. I mean, we have first established an integrated product development. We look from end to end. Yeah, that's how we start to design any product, especially the product that has won this award. And our goal is always to apply, some smartness and safety technologies as much as possible to ensure that the products are of high quality, reliable, and actually also satisfy the project's mission profile. What we do is we consider safety architecture on a very well established and proven platform. And we also understand the cause and effect relationship in product development, what are the failure modes, what are the failure mechanism, and what are the behavior behind that, and so on. So it's very important to understand the cause and effect relationship when we want to bring a very high quality product. So our key focus from the design perspective is on the requirements, what we call it as, intelligent sensing or self-sensing, intelligent diagnostics, intelligent maintenance, and also intelligent control. So that means there is a significant amount of innovation that goes into bringing this intelligence. And that's why we don't even call it as an inverter, we call it as a controller or a smart controller, incorporating all this intelligence.
That's fantastic. And I think to be honest, there are quite a few other things I'd love to ask about, from your perspective. But I think because we're running out of time a little bit, it would be unfair on the audience if we don't get to some of the audience questions. Why should I have the privilege of asking all the things I want to ask, I guess. So let's do some of these audience questions as well, if that's okay with you, gentlemen. And yeah, so Tim from the audience, thank you, Tim, for your question. So I think we briefly mentioned operating temperatures, didn't we, and conditions. So Tim asks how the increased operating ambient temperature impacts inverter efficiency. And for example, does the inverter cut out when more than 40 degrees centigrade of ambient temperature is reached, which I guess is becoming a more and more important consideration, unfortunately, with some of the, the weather conditions that some of us are becoming, unfortunately, more used to facing.
Sure. Maybe I can take this question. Basically, the ambient temperature is one part of the entire equation on what is happening in terms of the strategies related to, let's say, output power. And among these things, what is very, very important is the junction temperature of the power semiconductor. Yeah. There is obviously a defined influence between the ambient temperature and the junction temperature, but it also have some other parameters like input DC voltage, output loading. It depends upon what exactly is, let's say, the AC voltage and so on. So there is a significant amount of factors that plays an important role. And the product that is actually being designed to handle extreme temperatures, as we also see products installed around 50 degrees, as we showed before. And the most important thing that plays an important role in the equation is the so-called junction temperature. And there is a relationship between the junction to the ambient, but the key answer lies what is the power semiconductor's junction temperature to take on corresponding power regulation aspects here.
Excellent, thanks. And I mean, I don't know if this is also worth tackling then, slightly different but similar topic on temperature. So Dinesh, thank you for your question, asks, are there any temperature sensors or protection for the input terminals available with this inverter?
Yeah, there are some temperature sensors, as I have already mentioned, which are actually integrated inside the input side, in the DC side of the inverter. And these are the smart sensors, which are measuring, let's say, any kind of deviation or anomalies from the normal operating point. And when certain, let's say, range is exceeded, the inverter will detect it and will take necessary action to make sure that it does not become a hazard, basically.
Okay. And, you know, there's been quite a bit of talk about DC level string disconnection. And so, yeah, I mean, I recall when, you know, rapid shutdown requirements started to be introduced in the US market. I believe they're in place in Japan and a few other places. Do correct me if I'm wrong on any of these, by the way, Harry. I know that you know this topic way better than I do, of course. But so Joao from the audience, again, thank you for your question, is asking about the disconnection at DC level. Is it by string or by MPPT? My assumption is it's by string, but it's maybe a question for you rather than for me, I think, obviously.
Yeah, exactly. So the DC level is, let's say, measuring at different strings. Yeah, so we would measure at the input at the MPPT level what is happening, but the disconnection strategy is basically happening at the inter DC side. Yeah, so basically it's in order to protect the system. But there is actually also visibility and diagnostics information that will also tell what kind of let's say event has happened. Is it a reverse current, or is it an internal fault, or is it basically coming because of wrong polarity or reverse polarity and so on. So there is high amount of granularity, but I think the system fail-safe mode can only be achieved when it is actually happening at the inter DC side, basically.
Okay, that's great, and I hope that sheds light on your question there, Joao. So we had a couple of questions here as well regarding ride through for ride through events. Yeah, so again, I don't know if you can interpret some of the technical portions of these questions for the rest of us sort of media and non-technical folks, but Ashko asks if the SUN2000-330KTL grid support includes 0 voltage ride through, which they note is required in some countries for type D power plants, which is, as I understand it, power plants with a connection point to the grid at or greater than 110 kilovolts or below 110 kV, but with maximum capacity above the threshold specified by the transmission system operator. And I understand that varies in some different countries. But also, if we can just throw in one other question at the same time, because, you know, as we're pressed for time. So Murali asks, from a high voltage ride through or even low voltage ride through perspective, does Huawei prescribe any specific vector group for inverter duty transformers? I have to admit that goes a little bit over my head. So if you're able to tackle those,
no problem.
Yeah.
So perfect. I can talk about that. Actually, the inverters can do zero voltage ride through. So we are able to handle zero voltage ride through. We are able to handle multiple faults scenarios, asymmetrical faults. There could also be LVRT or the low voltage ride through that need not happen symmetrically, which is called as asymmetrical or unbalanced fault. We support all these scenarios. The same case is also true for the HVRT as well, where we also support. And the inverters can also support negative sequence current injection in addition to positive sequence injection. So we are able to handle any requirements that is happening globally right now or also in the future. There's no problem in that. And regarding, let's say, recommendation, basically everything depends upon from the point of common coupling to the inverter level, and there are certain kind of impedances behind or before that. And basically these impedances coming through cables or through the transformer will play a significant role. And actually at the utility scale level, there isn't anything called as zero sequence as most of the projects are doing, let's say, 3-wire connections. So there is no need to worry on this. And what is very important is to see that whether the inverter that you are going to choose is able to handle positive and negative sequence and able to handle the required grid codes, and also go beyond that, as there might be future changes that will happen very soon, also in Europe as well.
Excellent, excellent. Now, I think we're going to have to start winding down today's session, unfortunately. So a lot more great questions, and we thank everyone so much for being involved. But let's just do a couple more quick ones if we can, I guess. And so, from the audience, Sujavan asks, thank you for your question, by the way. Are these inverters already deployed on a large scale, or is it still in the developmental stage? So my presumption is that they're commercially available, but I don't know if you can tell us a little bit about the availability and, I guess how many of them sort of roughly you've got deployed in the field, I suppose.
Yeah, the inverters are already in the field. Various installations happening globally, even as I speak now. And the inverters, as I said, are able to handle different grid code requirements. So any projects that you are having in any part of the world having any specific grid requirement, you already have all the requirements satisfied, and you can reach us and get to know what models or softwares or power system components that you need for your projects. So the products are already there running in the market.
Excellent, fantastic. And finally, one topic that we are seeing so much more about in the last few years on PV Tech is the trackers. So not the MPPT, but the physical trackers, that the sun trackers, I guess you could say. Mm-hmm. We're seeing a lot more about that, a lot more investments. I think it was something that a few years ago people wrote off perhaps as being expensive or might not be as foolproof as might be hoped, but my understanding is that they are much more popular now than they used to be. So Chet has a question. Thank you for your question, Chet. Does the inverter range work with all commercially available trackers? But I don't know if you want to just, if you're able to use that as just, an opportunity to tell us a little bit about trackers and how it sort of interacts with those, I guess.
Yeah, sure. I can also tell a little bit overview on this. I think as I already shown in my slide, we use a kind of a tracking algorithm. We collect the string current, voltage, and power to obtain information like whether there's a shade or weather conditions, cloudy, etc., and the inverter finds an optimal angle for the trackers, and then it maximizes the yield this way. And in order to answer your question, what trackers, basically we are able to provide this additional information to any of the project using any of the trackers, and anyone who is willing to handle or to get this data is more than welcome, and we can integrate almost any tracker inside the system to have this added information for, let's say, increasing your harvest. So there is no limitations basically here. And obviously there are different manufacturers, different suppliers, variety of, let's say, players, and we are able to support anyone who is willing to handle this or who want to have this additional feature, the so-called smart DC system.
Absolutely, that's fantastic. Thank you so much, Harry. Okay, well, I guess it just remains for me now to thank both of our speakers, Harry and Lewis. And of course, to thank their organization, respective organizations as well, for working with us, Huawei and Decra. We appreciate your cooperation, support, partnership with us. But most of all, I think I can speak on behalf of all of us here at Solar Media and Harry and Lewis as well when I say thank you so much to all of you that registered and attended today. We had a lot of people on the call, a lot of great questions. And, from a personal point of view, I just want to say, thank you to all of you that work so hard in the industry. One that, is obviously so important for the society and for all our futures. And it's just, a great industry with some very exciting technologies involved as well. Let's never forget that, So yeah, just with that in mind, I just want to say thank you very much and goodbye to all of our audience and goodbye from myself and our speakers. Thank you.
Thank you very much. It was very engaging and exciting. Thank you, Andy and
Thank
Luis.
you.
That was great. Thank you so much, guys. Cheers.